We were talking already about scalar product because this is the key concept when we multiply matrices. But we can repeat, we can revisit what we know, and perhaps we can mention some more consequences, some more properties. So if we have two vectors, A arrow and B arrow from Rn, the scalar product is defined as AB as the sum of the products AI, BI, I running from 1 to n. It has some obvious properties. First, this is commutative. AB is equal to BA. If you take some number alpha and multiply the vector A and then compute the scalar product with vector B, then it is the same as if you compute the dot product. The scalar product also is sometimes called dot product. So we can factor out the scalar alpha in front of the dot product. Then it is distributive in the sense if we have two vectors A and B and multiply with C, then it is equal to A dot C plus B dot C for any three vectors A, B, C from Rn. Then if we multiply a vector with itself, A dot A, which is sum of AI squared, then you see this is definitely greater than or equal to 0, and the scalar product may be 0 if with itself, if and only if the vector is equal to 0. That means every component of it is equal to 0 exactly. And this allows us to introduce norm of the vector, sometimes denoted just A without arrow, being the square root of A dot A, which is the square root of sum of AI squared, I running from 1 to n. But this is also equal to AB cosine of phi, where A is the norm of the vector A, B is the norm of the vector B, and cosine and phi is the angle between the two vectors. This is easy to show if you consider the vector A and the vector B with components A1, A2, and B1, B2. And if we denote this angle alpha, this angle beta, and the angle between the two vectors phi, then we have a few obvious identities, namely A1 is A cosine of alpha, A2 is A sine of alpha, and similarly B1 is B cosine of alpha, and B2 is B sine of sine of beta, cosine beta, sine of beta. And then when we write AB cosine of phi, then phi is alpha beta, and this angle is phi, Then this is A, B, and phi is beta minus alpha. But cosine of difference can be written as cosine beta cosine alpha plus sine of beta sine of alpha. And then you see a times cosine of beta is a1, and this is multiplied by b cosine of beta, which is b1, plus a sine of alpha, which is a2, times b times sine of beta, which is b2. And this is exactly the definition of the scalar product. Because cosine looks like that, then it tells us that the scalar product may be equal to 0 even for non-zero vectors when phi is by half. That means if the two vectors are perpendicular, that means 90 degrees angle or pi half. Such two vectors are called perpendicular or orthogonal. Sometimes we work with complex numbers instead of reals. It could be possible to define the scalar product still as a sum of products, where the components may be real or complex numbers. But we like this property so much that we modify the definition of a scalar product for complex numbers, and we take the complex conjugate here. Then obviously the scalar product is no more commutative, because if you change the two operands, then you must take the complex conjugate here. Another generalization of the scalar product from finite dimensional cases are to infinite dimensional cases. Instead of pairs, triples, pentuples of real numbers, you can consider infinite sequences. Then some sequences have finite scalar product and some have not. Then usually we forget the sequences that result in infinite sums, and we work with sequences for which these sums are finite. Another generalization is from vectors or sequences to functions. Imagine two functions, say continuous in some closed interval. Then, instead of i's component of the vector, we can consider the function value in some argument x. As we can multiply the components of two vectors, we can multiply two function values of two functions. And then, instead of taking the sum of these products, we take, you guess? Now stop me for a moment, stop me, and think it over. How should we modify the sum when a and b are not vectors or sequences, but rather functions of a real variable? Stop me and think it over. Okay? You've got it? Integral. If we have two functions, say f and g, we can consider integral, we can consider scalar product in the integral from a to b of fx times gx dx. This is f, right? The sum naturally comes to integral. it may resemble Riemann sum, Riemann integral, okay? So yes, for two functions continuous in some closed interval AB, well now this A is not this A and this B is not this B, right? These are just limits for the integral. Two real values, A and B are now real constants. And similarly, as we say that two vectors are orthogonal or perpendicular, which makes sense even for infinite sequences. We can also talk about orthogonal functions. Just we say the functions are orthogonal if the scalar product is equal to 0. Consider the function, say fx is cosine of x and gx is sine of x for x from the closed interval, say from 0 to 2 pi. Strange enough, it turns out that these two functions in this interval, it's important to say what interval we mean, in this interval are indeed perpendicular, are orthogonal. If we consider the scalar product, then we have integral from 0 to 2 pi, cosine of x, sine of x, dx. And this is easy to integrate. If we multiply by 2 and divide by 2, we have 1/2 integral from 0 to 2 pi, and this is sine of 2x. And it is easy to find an antiderivative, which will be minus cosine of 2x half and when we factor out minus 1/4, then we have 1 minus 1, which is 0. So the scalar product of these two functions is 0, so we say they are perpendicular. So that was some consideration, some details about the scalar product that we have seen already. Yeah, perhaps we should not forget some physical application. There are many, but perhaps the first one is the mechanical work. If you apply some force over some distance, then the scalar product of this force with this distance, with this displacement, is the mechanical work. If the force is in newtons, this is in meters, this is in joules.